equipped course on dynamics and control of rotorcraft or helicopters. To control helicopter, you have to understand the dynamics of helicopter quite a lot, okay, and it is fairly complicated. It is something which is quite new for even people who are familiar with aerospace engineering. Even aerospace people actually don't know much about helicopter if they are just they have studied that in undergraduate. Okay. So here we have just a small model helicopter. Okay. At a suitable time I will show you, okay, why I have asked him to bring it here. Okay. And I will also pass it along at one point, because I would like you to see something, okay, which is very unique of helicopters, something called SWAS plate, okay, which I can remove this casing, right. Okay. So this has something called SWAS plate. Okay, we will come to this in a moment. Okay, so then we will talk about it more. Okay, so I will just keep it over here and I will start. Okay, so this is the overview of my two lectures, which is the current one and the next one. Okay, this is what we will be covering more or less. I will initially introduce some of the key features of rotorcraft technology. Mostly how helicopters fly. Okay, why should we study helicopter dynamics and control. Okay. Then we will go into a lot of aerodynamics, okay, because to understand the plant, that is the helicopter, we have to become familiar with the aerodynamics of the rotor, because the entire control of helicopter is done through rotor, and the aerodynamics is fairly complicated. So we will go very slow with this, and I would urge you to stop me and ask questions, okay, whenever things are not very clear to you, because I can imagine it will be very challenging for you, especially people who are from not from mechanical background and electrical CS department people. It's going to be intimidating for you a bit, okay, because there are a lot of maths, lot of equations, okay, but I will try to go very slow and systematically, and to help me further you have to ask questions. Okay. So we will talk about something called momentum theory, okay, for hover, forward flight. Then this is the key thing, blade element theory, which enables you to model the aerodynamics of helicopter rotors. Then we will go in the dynamics part. Okay. So aerodynamics is fine. Okay. Then we will talk about blade dynamics. I will introduce what I mean by blade dynamics. We will look at something called flap dynamics, lag dynamics, torsion dynamics, and then the coupled system. Okay. So this is more or less the recipe for today. Okay. So starting with the introduction, okay, about rotorcraft technology. Okay. So what I have done here is I have put pictures of various different types of helicopters. Okay. So if you see aircrafts, almost all aircrafts have same inherent feature. It has a mechanism for forward speed. So it has some thrust generating system, either a propeller or a turbofan engine or a turbojet engine, which just tries to propel the aircraft forward, and you have wings. Okay. So inherently all helicopters, rather aircrafts, are functionally same, but if you look at helicopters, there is wide range of them actually, and they are very, very different from each other, and they have different challenges and so on. Oh, of course, they are all driven by some big rotor, okay, which is quite like our fan, but so this is our advanced light helicopter ALH Dhruv, which is what we call as conventional helicopter. So it is single main rotor and tail rotor. Okay. So that is the conventional helicopter. Then we have coaxial helicopter. Okay. So coaxial is, you have two rotors spinning in opposite direction. So contra-rotating helicopter. These kind of helicopters are only manufactured by Kamov Helicopter company, which is Kamov Design Bureau in Russia, and India also buys quite a few of them actually, okay, because they are compact and so on. This is another unique design called tandem helicopter. So you have one rotor in the front, other in the back. Again, this is the only unique design, CH-47E Chinook helicopter made by Boeing. This is another unique design called intermeshing helicopter. Okay. This is made by Kaman helicopters, which is the name of the helicopter is K-Max. Now production for this particular helicopter was shut down in 2003. Okay. So Kaman was no longer going to manufacture this anymore, but recently they had to restart the production for this particular helicopter, and the reason is very strange. In collaboration with, so the Kaman Aerospace in collaboration with Northrop Grumman, they had made this helicopter fully autonomous or optionally pilotable. So you can fly this helicopter without a pilot sitting on board, and they use this quite a lot actually in Afghanistan for overhauling cargo and so on. So it's already getting used like a autonomous robotic crane, okay, which will lift something for you and transport it to some other location. So now there is a huge demand for this particular helicopter. Okay. So Kaman actually started production of this all over again very recently. So these are various types of helicopters, okay, what we call as conventional helicopters or pure helicopters I would say. Then there are a whole breed of upcoming VTOL vehicles, okay, which are hybrid helicopters / aircraft, which are trying to sort of combine the best from the world of aircrafts and best from the world of helicopters. So you have compound helicopters where you have rotor and there is no tail rotor in this, and you have propellers, and there are small wings also, stub wings. The idea is to make helicopters fly faster, and arguably these are already envisioned as the future of combat helicopters. So helicopters used by army, they would all be replaced by these kind of compound helicopters, because these helicopters are capable of flying at double the speed of existing helicopters because of some technological changes. Then you have already operational helicopter called V-22 Osprey. So this helicopter is not really a helicopter, it's actually a tilt rotor. So it's unfair to call it a helicopter. So the idea is that, I mean, you take off like a helicopter with the propellers pointing vertically upwards, and after takeoff, I mean, you transition and become a airplane, basically a propeller driven airplane, and this gives it a lot of strategic advantage. But then doing this tilting part is not very easy, okay? It's quite complicated, and there are issues with this particular vehicle, okay? But even then it is being produced and it is being used by US Army, Australian, Japanese armies and so on. Then there is another category of vehicles called autogyros. So here the rotor is not powered at all, okay? So rotor spins on its own like a windmill, and you have a small propeller which propels the aircraft forward, and this propulsion makes this rotor spin. So these are, and most of these designs are actually something which have been made and designed, I mean, long back, okay? Now there is a sort of a revolution coming up in the aviation sector in terms of personal aerial vehicles, air taxi systems, okay, systems which are going to change the way aviation is right now, okay? So right now we mostly see big aircraft flying from one place to another, but soon, I mean, okay, soon in the sense near future, probably 5 to 10 years from now, we would probably see a lot of personal aerial vehicles in our airspace. And this is an example from Lilium, it's a European company, Lilium Jet. So they have used wings and they have some kind of ducted fans which they turn up and down to propel this kind of aircraft, and there are many other designs. I mean, just last night I saw that Airbus aircrafts, or Airbus helicopters rather, they tested their own version of personal aerial vehicle called Vahana. So the Vahana is actually the same Vahana which we call, I mean, from Sanskrit, okay? I don't know why they called it Vahana, because I mean some of the Germans have some fascination for Sanskrit actually, okay? So they call it Vahana, and they tested its full scale prototype for single seater manned personal air vehicle. They have just done the hover testing so far, so they have their own design actually, okay, which has some similarity to this, but still it is different. So you can see there is a lot of work going on in the area of VTOL and rotary wing technology, okay? A lot of things are happening, and as a consequence, also so here, I mean, I put some small UAVs which at IIT Kanpur we are researching on, okay? So a lot of things which we have built, coaxial, small coaxials, this is a remote control boomerang, then we have our own convertiplane vehicle which we envision as actually a candidate for personal air vehicle in future, okay? So we built a small prototype, now we are trying to make a slightly bigger prototype and so on. Then this is our helicopter, okay, and probably you will get to see a demo of this also, okay, during the course, and lot of work we have done, okay, towards control of helicopters is for this particular thing, okay? And this is fairly advanced helicopter right now, it is fully autonomous, and we have shown it to army and many other people, okay? We are even taking it to Malawi in Africa to do trials for its usage for UNICEF for delivery of medicine in remote areas. And then we have also made this quad rotor, which is actually an engine powered quad rotor. It's a very unique thing, and right now you don't find many engine powered quad rotors out there. It's not a hybrid vehicle, so it's not like, I mean, we are generating power and we are powering rotor, it's actually direct driven. So there is a transmission which powers all the 4 rotors together. So this is just to give you an overview and background why we need to study rotorcraft, okay, and the control of rotorcraft. To study any of these concepts, we have to have understanding of the aerodynamics and blade dynamics. Okay. So now let us see, okay, how does a helicopter fly, okay, because several of you are actually from CS background, so I thought it is necessary that we briefly look at, okay, a very basic question, okay, how does a helicopter fly? Okay. So can anybody tell me how a helicopter flies? So it generates thrust, the rotor generates thrust which pushes it up, okay. So how does the thrust generates, that is the question, how is it generated actually? So, we have a fan kind of thing, blades which are spinning. So, it actually what it is doing physically is actually it is pushing the air downwards, and from principle of Newton's third law actually. Okay. So, for every action you have reaction. Bernoulli's principle is also involved in that in some capacity, because the energy change is actually in a particular manner. Okay. So, we will look at that, because Bernoulli principle is same as actually conservation of energy basically. Okay. So, we will employ that to study the rotor in a moment. So, it basically pushes the air down, and in that process it actually gets a reaction which makes it go up sort of. Okay. Now, how do you control a helicopter? So, I have a helicopter, how do I control? Okay. How do I make it go up and down or left or right, okay, forward or backward? How do I achieve that? So, for regular conventional helicopters, sorry, okay, this is achieved by tilting the tip path plane. Actually, there was animation, but after conversion to PDF it somehow is not working. So, we tilt this rotor tip path plane front or back or sides. Okay. If I do that, it will enable me to tilt the thrust vector in a particular manner. So, a component of thrust which is used to support the weight of the helicopter also gives me propulsion. So, that would enable me to fly forward, backward. So, if you see, helicopters are true 6 degree of freedom vehicles. They actually can fly in any direction and any manner. They can fly backwards, sideways, whatever way you want them to. And actually, when my student talks about his research, he show you videos where you would see helicopters flying upside down and doing all kinds of crazy maneuvers which you would never imagine a helicopter would actually do. Okay. So, it's this tilting of this thrust vector is actually achieved by what I was mentioning earlier, Swash plate. Okay. And then at the end you have also this tail rotor, okay, which is required, because when you spin the rotor there will be a reacting moment for that. Okay. So, to compensate for this reaction moment you have a tail rotor. If you do not have tail rotor, then you actually have to use second rotor. Okay. So, which would actually be spinning in opposite direction. So, if you see all these multi rotor concepts or twin rotor concepts, one rotor spins in clockwise direction, then the other rotor will be spinning in anti-clockwise direction. Okay. Because then the torque reactions from both of them are actually opposite, and you try to make them equal, so that your helicopter can maintain its yaw position, right. So, yaw is the direction which helicopter maintains. Okay. Okay. Now, I have couple of videos. Okay. Actually, this, okay, by mistake this has a wrong title. Okay. This should have been a different title. Okay. Sorry. So, here is actually a video of a very old helicopter which was made using tip jets. So, instead of normally an engine powering the rotor through a transmission system, this helicopter was powered by putting small jets at the tip of the blade of the helicopter. Okay. So, this is, if you put some jets here, okay, and make it spin, the video quality is poor. This is something I got from YouTube, but then it is very old thing. So, this actually gives a very nice visualization of the flow around the rotor. So, in forward flight what we see is actually the rotor behaves quite a bit like a circular wing. Okay. So, if you look at the flow field of a wing, you will see that there would be vortices near the edge of the rotor, okay, which are called tip vortices. And here if you see, even in the hovering flight, okay, the wake is convected nicely downwards. There is another video, okay, which shows you a close-up view of what is going on near the tip of the rotor. So, you have this huge tip vortex sitting there, okay, which you are seeing here in the form of a nice helical cylindrical form actually. Okay. So, here you see the tip vortices actually spin like that and they are convected downwards, but if you look at a particular plane and a location, you will see them being generated like this. So, the point I was trying to make by showing you these videos is that the flow field of helicopter is fairly complicated, okay, and you have tremendous effect of wake on the blade. Okay, there is a lot of blade and wake interaction, and there is also lot of circulation in the flow, there is a lot of unsteadiness in the flow, and so on. So, this is how it actually is, and now we have to see how we can simplify all this and make a model which will represent the flight of a helicopter. Okay. Let me go forward. Okay, I cannot go forward till I click outside. Yeah, okay. Okay, the videos have been switched. Okay, so the title was for that. So here I mean now is a very nice small video where the person actually shows you how a source plate functions. Okay, so this is again this is important for us because we have to understand how a helicopter actually is flown. Okay. So right now what he is doing is he is operating pedal and he is showing that how the pedal actually is changing the collective pitch of the tail rotor blades. So this is how you can change the thrust that the tail rotor is generating, because that will allow you to turn the helicopter in a particular direction. So make the helicopter yaw. Then this is actually a collective stick. When you pull the collective stick, it actually moves what is called source plate completely upwards. Okay. And in that process you actually end up increasing the pitch angle of each of the blades simultaneously, which increases the lift on all the blades simultaneously, and it will make helicopter go vertically upwards. So by using this collective pitch control you can actually make it go up and down. Okay. All those same controls are actually there in this small tiny toy helicopter also, exactly same controls. So if you work or study this kind of helicopter, you will actually get the understanding for the big helicopter as well, so at a much smaller cost. Then he has actually what is called a cyclic stick. So right now he is actually controlling throttle. So throttle, like if you rotate the throttle, so he is pulling the collective stick, and if you move the throttle, it actually increases the RPM of the engine. Okay. So it will give you more power in the engine. In between he had talked about the cyclic control. Let me go to that. Okay, where is the cyclic? That is collective. Yeah, so here is the cyclic stick. Okay. So when he moves the cyclic stick, that would actually tilt the thrust tip path plane or rotor tip path plane in a particular direction. So by moving the stick, if I move the stick left, my rotor will tilt towards the left. Okay. Similarly, if I tilt it to the to the right, okay, if I tilt it to the left, it will tilt towards the left. So can you just power it up and we can show it to them, okay, that how this is actually happening. So all that actually gets done by this source plate. So if I tilt my source plate, so you can see there are 3 servos on this, okay, 1, 2 and 3. So these 3 servos are there which are supporting this source plate, okay, and when I can move this. So let's power it up and we will show it by giving the collective and so on. Okay. So yeah, right. So we can now tune, right? Don't spin it yet. Okay, let it be like that. Okay, okay. We just want to show you. Okay, so give the collective now. Okay. So you can see the whole source plate is actually moving up and move it down. Okay. So what it does, if you look at the plane of the blade, move it up again. So it is changing the pitch on both the blades collectively, right? All of you can see. Move it up again. Okay. So if up, it again goes normal. Okay. So this is the collective pitch control. Okay. Now give a cyclic. Okay. So if you see the cyclic, now we have given a lateral cyclic which is tilting the source plate laterally, and in turn this tilting will actually change the pitch angle on the blade in a cyclical manner. Okay. So you see now when it is tilted, the blade which is actually on this side will not see any change in pitch angle, but when I go here, okay, one blade will have higher pitch, other blade will have lower pitch because of the tilt, right? Because this tilting of source plate actually also tilts my what is called pitch link. So these things what you see here are actually pitch links. So one pitch link is pushed up, other pitch link is pushed down. So one blade will actually see higher pitch angle and as a consequence higher lift. Other guy will see lower pitch angle and lower lift, and as a consequence all this actually will result in tilting of the thrust vector. Okay. How that is happening will become more apparent when we see the equation of motion for the rotor blade. Okay. And all that. Okay. So can you spin it a bit? Okay. We will see if we can show the tilting of the tip path plane also a little bit. Okay. Spin it here. Okay, so you have to keep it to your eye level. Yeah, spin it some more, okay, because it's too low, you will not be able to see. Maybe make it straight first, okay, make it straight completely. Yeah, give slightly higher RPM. Okay, yeah. Now give a forward cyclic so that it goes forward. Okay, yeah. So this, keep it higher, slightly higher. Okay. RPM. RPM, yeah, RPM should be higher. Okay. So right now it is actually, make it back again normal. So the cyclic 0. Yeah, spin it slightly higher. Yeah. Okay. Now tilt. Yeah. So you could actually see that even Right. So in this actually if you see very carefully it's somewhat hard to see because the background is quite white here. Okay. Anyway, fine, so bring it back to normal. Okay, so it's okay. So it's slightly difficult to see, maybe I will put a video later. Okay. So I was hoping maybe you will be able to see this, but the whole background is white, so it's getting merged in that. Okay. Anyway, so you saw the idea that how tilting of saw split actually would change the pitch angle of the blade in a particular manner, which will tilt the thrust vector in a particular manner. Okay. This will become more apparent when we see the equation and we see the outcome of that equation. All right. So that was about the introduction. Okay. So we have already have enough introduction about how there is the aerodynamics is fairly complicated. So beyond what you saw in the videos, there is also something called dissymmetry of lift. So when my helicopter is going forward, one part of the helicopter blade is actually moving into the wind, other part of the blade is actually moving out of the wind. As a consequence, there is dissymmetry of lift. So one side will experience higher velocity, so higher lift, and other side will see lower velocity, so lower lift. So this is called dissymmetry of lift. Then there is reverse flow. If your helicopter is going too fast, what happens? The blade which is moving away from the wind, so my blade goes up like this and it moves away from the wind. In that case, what happens? This may end up seeing velocity from the trailing edge to the leading edge. That is, flow will actually be in the reverse direction, because my oncoming velocity is very fast and my rotor going in this direction will actually end up resulting in slower velocity. So the net velocity will be negative. So this is called reverse flow. So normally the flow actually goes from do we have some chalk here? Okay, yeah. So if you have this as a airfoil, okay, normally my flow is from the leading edge to the trailing edge, but in some cases the reverse flow may happen, so your flow actually may be coming from the opposite side, which is not desirable normally. Then because of very high speeds, something called compressibility starts to happen. Okay. The moment your speed of blade starts reaching the speed of sound, something called compressibility effect starts to happen, and as a consequence you will have small shock waves forming near the blade. This further complicates the entire thing, and this also restricts the speed of the helicopter. This is the reason why helicopters cannot fly as fast as typical airplanes. So if you see, I mean, typical helicopter, the top speed of a helicopter is around 150 knots, okay, which is around 300 km/h kind of thing, okay, actually less than that slightly. Okay. But aircrafts, if you see, I mean, they fly at, I mean, if you see big Boeing 747, the top speed for that is almost 800 km/h, 900 km/h. Okay. So that is much higher compared to any helicopter, and the reason for that is this compressibility effect, because my blade is already spinning, and blade is spinning with a speed which gives you Mach number of 0.65. That is, the speed of the blade divided by speed of sound gives you around 0.6 Mach number. If you look at the commercial aircrafts, their top speed is around 0.78, 0.8 Mach number, close to 0.8 Mach number. So you see, you have very little room. Your tip speed will go beyond 0.8 Mach number at 0.15 Mach forward speed, right? Because 0.65 added with 0.15 will give you 0.8, which is kind of limit. If you go above that, your drag increases very high, becomes very high, and things become very uneconomical. So flying in such conditions is not affordable, okay, purely from the point of view of enormous drag you end up encountering. So because of all that, and then we saw blade wake interaction, how the flow was actually going up and down and so on, and there is a lot of interaction. So it's fairly complicated, and this we already mentioned, okay, because of this compressibility you cannot make helicopters fly fast, and that's why in the compound helicopter what they do is that they slow the rotor down to the speed, and that gives you more room to make the helicopter go faster. Okay. All right, so that was the overall introduction. Okay, any questions about anything?
Could you explain reverse flow?
Yeah, so reverse flow, okay, I don't have much room to draw. So what is happening is my blade is spinning, right, okay, like this, and you have flow. When the helicopter is going forward, you have some speed of helicopter, say V infinity, all right. So when the blade is in this particular position, if this is omega and you are looking at a station which is at a distance r, okay, from the axis of rotation, what is the total speed that you are going to encounter here? That is going to be equal to V infinity plus omega into r, right. When you go on the other side, this is going to subtract from that. So, you have V infinity which is again in this direction, and the blade is actually reversed now. So, I will draw the blade like this. So, this is on the other side, okay, when the blade has reached the other side. So, now this is my front and this is my back for the blade, and my wind is coming here with V infinity, and other wind is coming because of the rotation because of omega r. So, now it is going to be omega r minus V infinity. So, if this V infinity is greater than omega r, you have actually negative velocity, okay, which is called reverse flow. So, now my flow, this part of component is actually higher than this part of component. So, as a consequence my net flow is actually in this direction, from the back of the blade to the front of the blade. So, trailing edge to leading edge, this is basically my reverse flow. Okay. So, this actually ends up creating sort of a small pocket on some part of the blade. So, in the section of the blade which is closer to the axis of rotation, that will actually experience this kind of reverse flow. Okay. All right. So, that is reverse flow. So, now we will start with momentum theory. Okay. A very simple model for my helicopter rotor. So, in this cartoon what you are seeing is that my helicopter is in a hovering condition. Okay. So, my helicopter is stationary and hovering at one particular location, and in this to hover it is actually inducing some amount of velocity downwards. So, in this momentum theory what we are trying to do is we are trying to employ the fundamental laws, that is law of conservation of mass, conservation of momentum and conservation of energy. So, irrespective of whatever system is there, okay, these laws are always going to be obeyed. Okay. You cannot have any of these laws disobeyed, okay, for a natural system. So, this momentum theory actually assumes that this rotor is actually not made up of blades, but it is actually made up of a thin actuator disc. Okay. So, you are familiar with actuators, right, actuators and sensors and so on. So, here I mean we imagine that the whole rotor is actually like a disc which generates this velocity. Okay. So, it induces this velocity, and as a consequence there is a change in momentum which gives me thrust. Okay. So, it's somehow the thrust has come very faint. Okay. So, this is a thrust vector over here, okay. And beyond that there is also weight of the helicopter which is acting downwards. Okay. So, here I have just given the integral form of all these conservation laws, conservation of mass, conservation of momentum and energy. It may look fairly complicated, but you would see that I mean for this particular case it is fairly simple to apply. So, we also divide. So, this what you are seeing is actually representation of the physical flow which you saw in that video. So, when the helicopter was hovering, you saw that the entire smoke was actually going like this, okay, in a nice helical manner. So, instead of that helical flow, now we are assuming that the flow is nice and uniform. Okay. So, flow is very what we call laminar, and it is unidirectional. So, there is flow straight from top to bottom. Okay. There is no circulation involved and so on. So, we have simplified the actual mathematical problem to much simpler form of this actuators. So, the velocity induced at the beginning or at the rotor is Vi, which we call induced velocity, and the velocity which is being exited from the slipstream. So, now this boundary which we have created from 0, 1, 2, 3 up to here, okay, is actually called slipstream or the boundary of the flow, which you were actually able to see physically, right. When we saw the video, the smoke was actually giving us a very nice visualization of the whole slipstream boundary for the wake of the helicopter. So, we have that same thing here, and different areas. So, the area of the rotor is A, the rotor disc, okay, whole disc area. So, it is pi r square, r is the radius of the rotor, and this is actually far downstream. Okay. That is where the pressure of in the flow again becomes equal to the pressure, ambient pressure, that is atmospheric pressure. So, this is the point where we say that the wake is fully developed. Okay. So, it is way ahead or way downstream from the position of the rotor. Now, let us go to the same equations now actually applied to the system. Okay. So, earlier what you saw was just the integral form of the equation. So, conservation of mass is, so instead of just looking at the mass, we are looking at, because there is continuous flow of mass. So, we look at mass flow rate, which is d by dt of m. So, if m is the mass of air, so this is mass flow of air which is happening through the rotor disc, and because the mass has to be conserved, so whatever mass that is flowing through the disc at 1 and 2 should be same as what you see at 3. So, that is what we have here, rho a into Vi. A is the area and v is the velocity. So, v gives me the rate, right. So, that gives me mass flow rate. Rho is the density of air, rho a vi is going to be equal to rho a3 into w. W is the velocity of the air exiting this particular control volume which we have created. Conservation of momentum. So, what is the momentum that is leaving the system and what is momentum which is entering the system. So, my system is or control system starts from 0, this whole control volume. Again this point 0 is actually taken far upstream where the velocity of air is close to 0. Therefore, the momentum which is entering the system is actually 0 and the momentum which is exiting the system is m dot into w. So, that is why it is m dot into w is the momentum which is exiting the system, momentum entering would be minus of 0. So, which I have not put here, and this change in momentum should be equal to the force, and that force being applied on the system is actually T. So, this T is equal to m dot w, and that gives me a very simple way of estimating how much thrust my rotor is going to generate. Now, if I apply conservation of energy between 2 and 3 or between 0 and 1, I cannot apply the conservation of energy between 1 and 2 because that is where the work is being done on the system. So, energy is going to change, right. My actuator disc is actually actuating the air and causing some change in the energy of the system. So, if I apply between 2 and 3 or between the whole from the beginning 0 to 3 rather, okay, you see what is the change in overall energy. The kinetic energy leaving the system is half m dot w square and energy which is entering the system is actually 0 because again the velocity is 0, right. So, change of kinetic energy is half m dot w square minus 0. So, this change of kinetic energy produced in the fluid must be same as the work done by the rotor or my actuator disc. So, work done is your force into displacement. So, here it is basically power, that is work done per unit time. So, hence we have force which is T into Vi. So, this is my power, so or rate of change of energy if you would want to call it. So, T into Vi and that is equal to half m dot w square. So, these are very 3 simple relationships which we obtain by simply balancing the mass, balancing the momentum and balancing the energy for the entire system. This is the simplest possible model for a helicopter in hovering flight. So, what does this tell us? This now gives me, so if I just do a bit of jugglery with all these 3 equations, just a little bit of algebraic manipulation, I would actually get a relationship. So, from the mass conservation equation as W is equal to twice of Vi, or effectively my area here A infinity is actually half the area of rotor disc, okay. And further if I eliminate some other unknowns, I end up getting an expression for the velocity that my actuator disc is inducing, that is my rotor is inducing to the air to generate this thrust T. So, this Vi then is equal to square root of T thrust divided by 2 rho A, where rho is the density of air and A is my disc area. And I also call this as VH, which means induced velocity for hovering flight, okay, because induced velocity is a common term which I will have for hovering flight, for forward flight, for all kinds of things, okay. But VH we denote it so that we can differentiate it with any other flight condition, okay. Beyond that, we can also get an expression for power which is T into Vi, which we saw in the previous slide also, and Vi we already know what it is. So, using that I can actually estimate power which my rotor will actually require to generate the amount of thrust T and for the given geometry, that is given disc area. So, this is a very simple expression, okay, and this is very fundamental, okay, because using this simple expression you can actually do a simple design of a rotor for a personal air vehicle, or you can do it for a helicopter. You can estimate how much power the rotor is actually going to require. But if you compare this power from the real power for a actual helicopter, you will see that this number will be much smaller or somewhat smaller. Why? Because in this theory we have made lot of assumptions. We have ignored all the rotational flow, swirl in the flow, we have ignored many other things, we have ignored the effect of tip vortices, we have not even considered different blades, we are not considering the drag that the blade actually encounters, we are simply looking at an actuator. So, this is also called ideal power, that is, this is if the helicopter rotor was actually ideal, that is, instead of testing it in a real world, if you test it in an ideal world, this is the power it is going to consume. So, this is the lowest value that a rotor can actually have, lowest power value that a rotor can actually consume. So, this is just very simple thing, it gives me one very key information about this induced velocity. and this actually is very important. Induced velocity is always very important. There is huge amount of research even going now right now, okay, to come up with better ways of estimating this induced velocity, okay, and this is the simplest possible way. So all this theory which you are seeing actually was developed probably 200 years back. So of course there were no helicopters flying 200 years back, so why did we develop this theory for? Can you imagine what could be source of this theory? Say that again.
Ships.
Exactly, ships. Okay, so your propellers, okay, ship propellers and rotor blades are not at all different. Okay, so all this theory actually has been adapted or borrowed from whatever was developed for ship propellers, okay, long back. So that's why this theory is actually fairly almost 100-200 years old or even more probably. Okay. Now before we proceed further, okay, I am going to introduce some lot of new parameters, okay, which you probably are not familiar with. Lot of non-dimensional parameters, because normally in engineering whenever we want to compare two systems we do the comparison for non-dimensional numbers, because if you see a big helicopter, okay, will actually have higher power consumption, a smaller helicopter will have a smaller power consumption simply because of the size and scaling. But then how do I know which one is actually more efficient, which one is lifting more weight? So to do a comparison in a meaningful manner we introduce many of these parameters, okay, such as thrust coefficient. So this is Ct, okay, so thrust divided by a certain parameter which is density of air, disk area and omega into r. So normally for in helicopter community whenever we non-dimensionalize things, so any dimension or any which has the dimension of length is divided by the radius of the rotor. Any parameter which has dimension of velocity is divided by tip speed omega into r, because these are very important design parameters for the helicopter, okay, the speed of the tip omega into radius of the rotor. Similarly all the force components may be divided by this, so that is rho a omega r square, and that becomes thrust coefficient, and typically this number actually lies between 0.004 to 0.014, okay. And what value of Ct your rotor is operating at tells you whether the helicopter is heavily loaded or less loaded. So 0.004 would mean that the loading is less, 0.01 is fairly high loading, okay, because higher loading also means the blade may actually end up stalling, you are reaching the limit of the helicopter to lift a particular weight, okay. Similarly we define power coefficient Cp, which is power divided by rho a omega r whole cube. Another parameter is torque coefficient. So as from a control point of view you are more keen on thrust and torque, okay. Power is not that relevance for you, okay, I mean most of the time, okay. Probably from the point of view of actuator saturation and all you may probably want to see that, but other times I mean we are more interested in the force producing agent, okay, and which is of course relevant for my control, and torque, because that is also something which is going to be used for control. So if I have to control my helicopter any motion, okay, I am typically going to modify the thrust and the torque, because that is what is going to change the attitude of my aircraft. So similarly we have this torque coefficient, so it is similar to this q rho a omega r whole square into r, and incidentally both these guys are actually same. Why? Because this p can be written as q into omega, torque into rotational speed gives me the power of my rotor. So if you substitute p equal to q into omega you will see that you will get exactly same expression. So non-dimensional Cq and Cp are one and the same thing, but when you make them dimensional they may mean slightly different, because they will have different units and everything, okay. Just push the door. Then we saw induced velocity, okay. There is a non-dimensional form of this induced velocity which is called lambda I, okay. So earlier we are using Vi, if I divide this Vi by omega r, omega into capital R, it becomes lambda, okay. So you will see this lambda quite throughout, okay, and it is quite important actually also. You will see for even control of quad rotors it becomes variable pitch quad rotors, it becomes very important, which Dr. Kothari will be probably introducing later in the afternoon today. So this actually becomes a very nice simple expression. So whatever we had earlier Vi equal to square root of t by 2 rho a now has become lambda I or lambda h equal to square root of Ct by 2, okay. This is fairly useful thing. Also before I proceed further, okay, all of you have laptops with you, okay, all of you have MATLAB on that, everybody has MATLAB, okay, no, okay. So how many people do not have MATLAB on your laptop, or you do not have laptop at all, okay. 2, everybody else 3 people, okay. Everybody else has MATLAB and laptop, okay. So we will try to arrange MATLAB and laptop for you, because for our tutorial we would actually make you do some small coding in MATLAB, okay, so that you can do some simple calculations and see, get familiarized more with this kind of thing, okay. It will be of course very new for you, because you have not done much of aerodynamics, but it will be nice, okay. It will be a good learning experience for all of us, okay. So we will require 3 laptops with MATLABs, okay, fine. Okay, so then we have power coefficient in terms of CT. So this, I mean, you can ignore this, this is just the intermediate step. So CP then comes out to be CT raised to power 3 by 2 by square root of 2. So this formulas which we saw earlier, which looked slightly intimidating, is now looking far more simpler. So CP is simply, so this is again ideal power. So ideal power coefficient is, or even CQ, you can see CQ would be equal to CT to the power 3 by 2 by square root of 2, and this is also same as CT into lambda h, okay. Beyond that there are 2 other parameters which may not be that relevant to you, but I nevertheless I just put it there, because these are more critical for design of the system, not really so much for the control. So there is something called disk loading, which is thrust per unit of area. In aircraft community we have something similar which is called wing loading, that is your thrust, or rather lift, in that case lift divided by the area of the wings. So here we have thrust divided by the area of the rotor disk. Then there is another parameter called power loading, which is thrust by power. This is a measure of efficiency of a rotor. So higher power loading means better, which means my rotor can lift more amount of weight for same amount of power, okay. So this is, you want this to be higher power loading. Disk loading, I mean I will not go into the details of that right now, okay. So that is the thing, okay. Now I can extend this same momentum theory, okay, to other scenarios, okay, that is climbing and descending rotor also. I can do the same kind of moment equilibrium, mass equilibrium, and energy equilibrium, okay, and that will give me expressions for induced velocity for the rotor for this climb case and for descent case, okay. Now these things are actually important. They are important because if you, even if you are modeling a quadrotor for example, okay, when a quadrotor actually starts to maneuver, what happens if my quadrotor, okay, which has 2 rotors on this side and 2 on the other side, if I make it roll, okay, if I make it roll, what happens, my 2 rotors are actually going up and other 2 rotors are going down. When I am trying to make a quadrotor go forward, my front 2 rotors are actually going down and back 2 rotors are going up. So what happens, this, the front rotors actually are in descending flight, the back rotors are actually in the ascending flight, and you can see the induced velocity for both the cases are very, very different actually. So this is actually relevant. This is a case of climb, when my rotor is actually in axial climb, nice perfect axial climb. Then my induced velocity in terms of my climb velocity which is Vc, and in terms of my hover induced velocity Vh, which you have seen earlier, right, it was square root of t by 2 rho a, right. So in terms of Vh and Vc it comes as a quadratic like this, okay. This is for the descending rotor. Now this is only valid for a particular scenario. Now when the helicopter, okay, goes in descending flight, there is some problem which happens, okay. Now when it is hovering it is fine, okay, air is coming nice smoothly downwards. When it is climbing it is also fine. Why? Because my air is being pushed down by the rotor downwards. When it is trying to go up, the speed of the air, which is ambient air, which is coming or entering the control volume, is also in the same direction. So all the 4 flows are actually in the same direction, they add up and it is just nice uniform flow. The flow remains nice and uniform just like it was there in hover. But when I start descending, there is an issue, okay. And what is that issue? My rotor is trying to push the air downwards, but my helicopter is trying to go down. As a result, the relative velocity of air with respect to the helicopter is actually from down to up. Rotor is pushing air up to down, and because of motion of helicopter the air is coming from down to up. So you can see that overall everywhere in the flow there would be locations where the flow velocity may be 0 at some places, it may be down at some places, it may be up at some other places. So then our main assumption that the flow is nice and uniform in one direction everywhere in our control volume is no longer valid, okay. And making that assumption would give you huge error, and as a consequence we actually cannot apply this simple momentum theory up to the speeds where Vc by Vh is 2, that is The reason for this number 2 is because I mean my W here, okay, remember W here was twice of Vi, right. So unless and until I overcome that velocity twice of Vi, I cannot ensure that my flow is going upwards everywhere in the control volume, and that happens. So if my descent velocity is more than twice of induced velocity of a hovering rotor, only then I can ensure that I can apply momentum theory. But then in real world helicopters do not descend with this kind of velocities, okay. This is just a physical number, just a mathematical number rather, okay, and does not have any physical relevance. So what do I do if I want to find out the induced velocity for much smaller rates of descent? Then we have to resolve to one of these empirical expressions, yeah, because there is no simple theory which will enable you to estimate the induced velocity in those regimes, and actually those regimes are very bad. So normally if I make a quad rotor descend very quickly, how many of you have flown a quad rotor? Nobody has flown a quad rotor? I was hoping somebody would have flown a quad rotor, okay. So next time when you go, okay, I mean after finishing this course when you are going back, okay, if you have a son or a daughter, buy a quad rotor for them, okay, from the mall on your way, and please fly it yourself. So you will see, if you, when you are trying to land the quad rotor, if you come too fast, the rotor will just lose its control. Helicopter, I mean the quad rotor will actually behave in a very weird manner. That happens because something called vortex ring state, okay, and that is why I was asking, because if you have flown you would have definitely experienced this, because any new pilot, okay, who has not flown quad rotor a lot, he would end up coming too fast and the rotor will actually lose control. So normally all these vehicles are designed, okay, to descend at very very slow speeds. So if you go and fly a DJI Phantom, okay, you would have seen DJI Phantom in many marriages, people are now using it to shoot videos of marriage parties and so on, right. So in those, I mean they have built in the controller, they have implemented this capability that whenever you make it come down, okay, it will always come at very very slow speeds, okay, it is limited, you cannot make it come faster than that, and that is based on this problem of vortex ring state. If it comes any faster than that, it will actually lose control. Lose control means I mean nothing can be done, nothing at all, okay, because the aerodynamics is such. So when you are descending at low velocities, okay, low controllable velocities which are, so normally you never want to descend at velocities more than 0.1 or 0.15 of the hover induced velocity. So you can, if you know the weight of the vehicle, so in this case, okay, let me go back here. So for this, all these formulas, okay, what we saw, sorry here, okay, what is this T actually? When you are hovering, this is actually same as your weight of the helicopter, right. So if I know the weight of the helicopter, I can very easily find out what is my induced velocity Vi and Vh, okay, and once I know that, I in my control design I must ensure that at any point of time none of my rotors should actually descend at speeds more than 0.1 of this Vh, okay, to be on safer side, because the moment you go at speeds higher than 0.1 of Vh, your rotor has a tendency of entering vortex ring state, okay, and then the control becomes very very difficult because the aerodynamics is too complicated actually, it becomes very unsteady and very strange. I have not included the videos of, I mean what happens on that and so on, because we do not have so much of time anyway, but that is the key thing. So in such scenarios, if I have to find the induced velocity for my calculation, I will either use this linear expression or this quartic expression, okay, and all the terms are known. So people have done a lot of wind tunnel tests, okay, in a controlled manner at NASA and so on, and they have found out these approximate fits which gives you some estimation of what kind of induced velocity you will have, okay. So this is what we will use, okay. So now we understand, okay, what is this inflow or induced velocity, okay. So that was for hovering flight, okay, hovering and axial flying for the rotor, but then my helicopter not just does hovering flight, it also does forward flying, right. So what happens in forward flight? So I can do the same thing what I was doing momentum theory, I can apply also for forward flight, because forward flight is relatively benign, okay, compared to climb and descent. The reason for that is the moment I start going forward, there is large amount of air which starts entering the rotor, and this large amount of air actually makes this required induced velocity smaller, and as a consequence if you see any helicopter and if you look at how the power changes with speed for a helicopter, initially power is fairly high, then with speed it will come down actually, okay. So it will come down, and then beyond a point when you start to go at higher and higher speeds, the power will again increase. So the power curve for helicopter is like a bucket, so we call it power bucket, and you normally want to fly your helicopter at the minimum speed. So even when you are doing a control design for a helicopter which you want to fly for highest range or highest endurance, then you will choose speeds which will actually ensure. So, even when we have designed our helicopter autopilot, in that we look at that that what kind of speed should I choose for in my autopilot to ensure that I have maximum range. So, which is important for your flight management system and so on. Alright, so I can do the same kind of momentum balance. So, here now the velocity is coming at an angle with the rotor disc, because to make my helicopter fly forward I must tilt it forward, because what happens, my rotor tip path length first tilts. When the rotor tilts, actually my helicopter will also have to follow that. So, it will attain an attitude like this and it will flow, go like this. So, that is what we have here. So, actual thing would be somewhat like this: your thrust is tilted, or rather disc is tilted and the flow is coming straight, but instead of that I have turned this around and I have made the rotor vertical and the flow at an angle. So, this one and the same thing. So, I can do the same thing. This was done first by Glott. So, he did the momentum theory analysis, same kind of things he did, energy conservation, momentum conservation and so on, and what do we get from that. So, again, so as you can see, this momentum theory just gives me information about how much of velocity needs to be induced by the rotor, because again still right now our rotor is actually not something which is made of blades, it is just a disc which is imparting a momentum to air around that is all. So, that gives me the, so now I mean we should also introduce a key parameter called advance ratio mu. Similar term is also used for propellers, but that advance ratio is slightly different in definition than what we use here in aircrafts, in our helicopter. So, this is defined as your free stream velocity cosine of alpha. So, alpha is the angle made by the helicopter with the vertical, and omega into r, so tip speed, because we are non-dimensionalizing. So, this is a non-dimensional parameter which represents the speed of the helicopter. Typically, any existing conventional helicopter cannot fly beyond speeds of 0.37, 0.38 in terms of advance ratio. That is the limit for all helicopters, because of that compressibility effect and so on. So, this is advance ratio, and using this advance ratio we can find out from this momentum theory calculation that lambda, my induced velocity, would be actually v infinity sine alpha plus induced velocity, which the rotor is inducing. So, you can see my total inflow is now combination of the flow of the air which is coming through the rotor because of the motion of the helicopter. So, that is one component, and the second component is the part which is the rotor is inducing. So, both these together are now going to support my weight. So, as a consequence, the requirement for this induced velocity decreases actually, and that is why my power actually decreases initially. So, this on further simplification gives me a nice expression like this. So, this lambda I turns out to be Ct by 2 square root of mu square plus lambda square. This mu square plus lambda square comes because this gives you the resultant velocity. So, you have your induced velocity from the rotor at an angle which is at some angle, and this forward speed v infinity is at a different angle from that. So, to find the vector sum of that, you end up doing mu square plus lambda square. So, I have skipped all the derivation and everything, but this is what we end up getting. And compared to the previous cases where it was fairly simple, if I know the weight of the helicopter, I know the induced velocity. Now, knowing the weight of the helicopter is not enough. Why? Because this equation is a nonlinear equation. You have lambda here and lambda here. So, there is no exact solution for this. I cannot solve this directly, but then it is very easy to solve. And in our tutorial, we will just first do this actually. Today in the evening, we will try to see how you can write a small code, just probably 20-25 line code, which will allow you to calculate this lambda for a given Ct. And you can use either fixed point iteration or Newton-Raphson method. And in Newton-Raphson, if you employ, it gives you answer in just 2 or 3 steps maximum. It's fairly fast, and this is the approach which we use for Newton-Raphson. So, I have actually given both the approaches rather here. So, in fixed point iteration, we start by assuming the lambda to be some lambda 0, which is whatever the value is for hover, and then for a given value of mu and given value of alpha. So, these are parameters which I would give to you, that tell me what will be my lambda for a value of mu and a value of alpha, and of course Ct, because what the lift, or rather the weight which the helicopter has, that will determine the amount of Ct which you have, and then you can actually solve this. So, I start with this guess and I use this particular guess over here. So, this is now lambda 0 and I will get lambda 1, and I just repeat this in a loop, just in a simple for loop, and I will actually get the answer probably in 8 to 10 steps. But if I do the same thing with Newton-Raphson, define my function f lambda as lambda minus mu tan alpha minus this, and do the iterations in the same manner. This will actually give me answer in a much faster way in 2 to 3 steps. Now in a control design, normally we want our solutions to be closed form and deterministic. Okay. I mean, if your solution is not attainable in a certain amount of time, it may actually help you, I mean it may create some problem for you to do the control design, but I believe, I mean, this is fairly robust, and for almost all kinds of problems in 3 steps you can definitely get the answer. Okay. So it is not like something you have to wait for 20, 100 iterations or so on. It is very simple equation from the point of view of convergence. Okay. So it will converge immediately in short steps, 2 to 3 maximum, okay, and we will check that also, okay, in our tutorial. Okay. So that was the whole thing about the momentum theory. Okay. That is how you, so momentum theory right now is only telling us, I mean, what is the induced velocity which the rotor must produce to support the weight of the helicopter. Okay. But then right now it does not tell me anything more than that, okay, how my thrust is changing for a particular pitch angle, because to control my helicopter I must know what is the relation between my pitch angle and my rotor forces, okay, both my thrust as well as my moment. So to understand that, we have to go to something called blade element theory. This is same as also what people in aircraft community call strip theory, okay, because there also something similar is there. So in this what we do is we divide. So now we start looking at the blade itself. Earlier we were not looking at blade at all, okay, we are just looking at a disc. Now we will see, okay, what is happening actually on the blade. So this is a general diagram of a rotor which is spinning with the angular speed omega, or omega r in this case, okay, and at any particular azimuthal location. So this angle psi here, okay, which you see. So the convention for helicopter is that we define the 0 axis at the tail of the helicopter. Okay. So this is my 0, and any angle is measured from that. Okay. So right now this is showing the blade at an angle psi, and psi is the symbol which we use. Okay. So it is called azimuth angle of the blade. So at this particular azimuth angle psi, my blade, or a segment on the blade rather, would be seeing various velocities. So it will be seeing a component of radial velocity, it will be seeing a component of normal velocity, and so this is normal to the to this blade longitudinal direction, and beyond this there will be a third velocity which will be actually going into the blade, okay, sorry, into the plane of the rotor. So that we will see probably in the next slide, and as a consequence, I mean, there will be some forces also acting on the blade, okay, and typically any force which is acting on the blade may be resolved in 3 components. One would be the chord wise component, which is along the chord of the blade. Okay. So the chord of the blade is basically, if you make a cut, okay, this distance is chord, okay, the chord of my blade. Okay. So this is the chord wise direction. Then we have vertical direction fz, which will be coming out of the plane of the rotor, and other will be actually in the radial direction. Okay. In this case, I mean, they are shown in a slightly different way. Okay, sorry about that. Okay. Anyway, now here it is far more clear and better for us. So like we saw earlier, okay, we have a tangential component of the velocity called ut, which you saw here. Okay. So this is my ut, okay, and there is a perpendicular component of the velocity or normal component which is called up. This up is actually, you can see, is a combination of the induced velocity from the rotor, which we saw from the momentum theory. Okay. So this is the induced velocity, and if my helicopter is in climbing flight, then you have a Vc also, the climb velocity. If the rotor is in hover or any other condition, you may not have Vc, okay, you may have something else. Okay. So you may have a contribution from mu tan alpha or something like that, okay, if you are in forward flight. So now we have this, so this is a particular section of the blade. So you can see the airfoil here, and what velocity it is experiencing is the normal velocity and the tangential velocity. If I do the combination of both this, do a vector addition, you get the resultant velocity like this. So air is coming at this particular direction, and the angle made by this direction of velocity and the chord of the blade is what is called your angle of attack. And this angle of attack, because of this, there will be some force. So if I put a wing, so this is just like a wing, right? So the difference between a normal aircraft and a helicopter is that now your wing is rotating. So that's why we differentiate this with by calling it a rotary wing. Other case is your fixed wing. Okay. So here we have the wing at an angle of attack, so this wing will actually end up generating some lift. So this lift is going to be normal to the direction of your resultant flow. So you have a lift, and in the direction of the flow you will have also a drag. Okay. So you have lift in the direction of flow, sorry, in the direction normal to the flow, and you have drag in the direction of the flow. These two forces can now be resolved in some other direction which is of more convenience to us, that is the vertical direction, because this vertical force is going to be my thrust. Okay. And this axial force, or rather the in plane force d of fx, this force is actually of relevance to me because this will help me find out how much torque my blade is going to require to make it spin. Okay. So this is also important to us, and this angle which sort of gives the relationship between my perpendicular and up and ut. Okay. This is called induced inflow angle phi. The symbol used for that is actually phi, and it is called induced inflow angle. So this angle we will see next is actually given as tan inverse of up by ut. Okay. So up was my perpendicular component, ut is my tangential component, and this up and ut may change depending on the level of model I am going to look at. So this same blade element theory now, which we are looking at now, can be used to model aircraft or a helicopter rather, okay, which is in hovering flight, okay, it is in forward flight, or is it in maneuvering flight, any kind of general maneuvering flight, even flying upside down. So this same formulation, same theory can be applied to model my rotor in any kind of flying condition by simply modifying this up, ut, and this third one ur. Okay. So depending on the flight condition, these velocities will get modified, but the overall fundamental principle remains the same. Okay.
What is this Vxyc? Ut is equal to.
Oh, this okay. So this is actually if my helicopter is flying in a general direction. Okay. My helicopter may be actually flying in any arbitrary direction, so the component of the forward velocity will be here. Okay. Okay. So this is some general component, but normally it will not be there. In this will not be there. Okay. You will only have this. Okay. Likewise, what we see here, okay, v infinity. So it is sort of that same v infinity. Okay. All right. So these are the forces, and these are the velocities which are there, and like we discussed, we can resolve these forces lift and drag to in the direction of normal force and my chordwise force, and these forces are for a particular blade element. Okay. So this is for one element of blade on the whole, out of the whole blade, I mean we are just considering one small infinitesimal element. Now I can add the contribution from all the blades. So if the number of blades is nb, then the thrust produced by similar element on a different blade, all of them if I combine together, my total elemental thrust becomes number of blades times the vertical force. So that gives me infinitesimal thrust, and similarly I can get the infinitesimal torque. So this is my axial force or the chordwise force Fx multiplied by the moment arm y. So if this particular station is at a distance of y from the axis of rotation, then y times dfx gives me the net moment, and nb times this net moment will give me the total moment because of all the blades combined. So what is this dl now? The dl is given by half rho ur square, the resultant velocity square, chord, c is the chord of the blade at that particular location, and cl is the lift coefficient. So lift coefficient is normally given as cl alpha into alpha, which we will see later. So this is the lift coefficient for the, so this is something which you get from the airfoil properties. So if I know what airfoil is there on my blade, I can just do a Google search and it will tell me what is the cl for that particular airfoil as a function of alpha. Similarly, I can get the CD for that particular airfoil as a function of angle of attack alpha, which you saw earlier. So, right? So this alpha which I have mentioned here also. Okay. So alpha equal to theta naught, which is my pitch angle, minus phi, which is my induced inflow angle. Yeah. So here I forgot to mention that the blade is pitched at a particular angle theta naught. Okay, and it has two components. One part is angle of attack, other part is your induced inflow angle. So theta naught minus this phi gives me alpha. Okay. So that gives me the angle of attack. This is the key difference between an aircraft and a helicopter. If you go to an aircraft, there is no phi over there normally. Okay. You may have a small phi because of some tip vortex presence and near the tip of the wing, but beyond that normally it is not there. So if you set the wing at a particular pitch angle or incidence angle, the angle of attack remains the same, it does not change. But here, because of this induced velocity thing, this angle comes into picture. So, even when my blade is pitched by say 16 degrees or 20 degrees, my angle of attack may actually only be 10 degrees or 12 degrees. Okay. So, this is a key difference between a helicopter and an airplane. Alright. So, that gives me my elemental lift, elemental drag, okay. Rho is my air density, UR is my resultant velocity between UP square plus UT square, and these are given for a particular case, but this may be changed, okay, depending on the scenario of the flow, and phi is tan inverse of UP by UT. But what happens is actually in real world, I mean this UP is typically significantly small, even though in the picture it is shown in an exaggerated manner, this UP is far less compared to UT, okay, because if you see omega into r is a much larger velocity component compared to the induced velocity from the rotor. So, this angle is often very small, and we approximate this by replacing this with UP by UT. So, instead of saying tan inverse of UP by UT, it is almost same as UP by UT. Yeah. So, that is what we will use and simplify everything later. So, this is the total thrust and total torque. So, number of blades multiplied with the lift and drag expression, and similarly here. Okay. So, if I apply this small angle assumption which I mentioned, that is phi is tan inverse of UP by UT is same as UP by UT, okay. And also because UP is much smaller, the perpendicular component is much smaller than the tangential component, I can approximate my net velocity by simply UT, that is also fine. So, if I do those approximations, and if I see here this dt, this drag is a small thing, okay. So, normally the drag is an order of magnitude less than the lift, and this angle also is a order of magnitude less than 1. So, you are multiplying two small quantities compared to one this large quantity, and this angle is also close to 1, sorry, this cosine of phi is close to 1. So, I can simplify this thrust calculation by replacing this entire thing by dt equal to nb into dl. So, I have to simply multiply number of blades into the lift. But for torque, this L is multiplied with a small thing, and this cosine here is large, and dd is a small thing. So, I have to retain the whole thing. So, my torque actually is number of blades into y into dl into phi plus dd. So, this is the simplified version of my thrust and torque calculation, and in reality if you do this calculation for any realistic helicopter, you would see that if I do not make this assumption, or if I make this assumption, the answer does not change, okay. That is why this approximations have been made, and they are fairly valid approximations. Now, converting to non-dimensional quantities. So, like we discussed earlier, we divide everything with length dimension by r, velocity dimension by omega r, and so on, and eventually I can convert my thrust to thrust coefficient, torque coefficient, and so on. So, going through all this maths, simplifying everything, I finally end up with an expression for dct in terms of something like this. So, now we are introducing another new parameter called sigma. So, this dct is equal to half sigma into CL into r square dr. Okay. So, CL is same as before, this r is now my non-dimensional radial location. So, earlier I was using y, which was dimensional quantity, now y divided by r. So, now this r will actually go from 0 to 1, right. And what is this sigma now? So, this sigma is actually called solidity of a rotor, and it is defined by ratio of your blade area divided by the disc area. So far in the actuator disc theory, we are only looking at the disc. So, our A was actually pi r square, but in the blade element theory, my total lift will depend on the area of my blade itself. So, what is my area of the blade? If I assume the blade to be rectangular, it will be radius of the blade multiplied by the chord, assuming the blade is rectangular. So, that is what it is here, okay, and multiplied by number of blades. So, r into c into your NB will give you the area of the blade and divided by pi r square. So, it will be NBC into r by pi r square. So, r goes away and you are left with this. So, NB into C by pi r. So, this is the solidity of a rotor. It is typically fairly small, of the order of 0.05, 0.06 and so on. Okay. Most of the rotors actually have low solidity, but if you compare this to a fan, not this ceiling fan kind of thing, but if you look at a table fan, okay, table fan has typically very high solidity because your blades are short and wide. Even marine propellers, okay, they normally have very high solidity. there may be propellers which may have actually solidity more than one, because the propeller whole thing is actually wrapped around and there may be overlap between each of the blades. So, it may actually end up with solidity greater than 1, but for helicopter or your core rotor propellers or any ducted fans and so on, normally this is going to be a small number, okay, fairly small number. Alright, so now we have a new definition for this DCT in a very nice compact form, sigma CL into R square. CL is my lift coefficient. Similarly, I can write expression for infinitesimal torque, half sigma phi into CL, phi is my induced inflow angle, CD is my drag coefficient into R cube dr. And now if I integrate this over 0 to 1, because now we are in non-dimensional domain, so my integration goes from 0 to 1. So, I can integrate this and I can get my CT and I can get my CQ. Yeah. So, this is my total torque and this is going to give me my total thrust. Yeah. So, in this if I see if I know my airfoil, I will know what is my CL, I will know my sigma because I know the geometry of my helicopter, I will know the CD, R is something which is just a parameter in the integration, what I do not know is just lambda. Okay. So, now normally to get this lambda, either we use the momentum theory which we saw earlier, okay, that is the simplest possible approach, or I can use more complicated things. I will give you one example of a slightly more accurate way of calculating this inflow, because in momentum theory my inflow is uniform everywhere in the rotor, it is constant everywhere, same amount of induced velocity is produced by every part of the rotor, which is not at all true. Every part will actually generate different amount of inflow, and so there are many ways by which we can estimate this, and there is lot of research actually still going on, as I mentioned, to come up with better ways of estimating this inflow. But for control people, I think using something like this is good enough, okay, just for control design. But then if you are going to do a validation of your control design for with a more higher fidelity model, then we may have to employ something better. So, I will give you example for that also probably in a while. Alright, so I can calculate now my thrust coefficient and torque coefficient. To get that, okay, CL I said, okay, if I know my airfoil, I can see it to be CL alpha into alpha. This is the most common approximation which is done. So, this CL alpha is my lift curve slope. So, normally the lift of any airfoil, okay, varies, it increases, then it becomes constant and then it will drop actually. So, the drop signifies something called stall. So, beyond a particular angle of attack, the lift will not increase, but then up to some point it is actually linear, fairly linear, and that linear part, if you are operating in that linear part, then I can approximate the lift generation by CL equal to CL alpha into alpha. Also this is only valid for a symmetric airfoil. For a cambered airfoil, you will probably also have some beta here, okay, plus beta or minus beta, but then for simple calculation this is fairly good enough, okay. It does not make any such a difference, it does not make such a big difference. So, if I use CL equal to CL alpha into alpha, and for CD I can use a constant drag. So, or you can even have a function for drag which is called drag polar. So, you can have a quadratic function for drag, but for most practical purposes we use CD equal to CD naught, which is a constant, and it gives fairly accurate answer, okay, for most reasonable calculations. So, once I know these two things, I can actually put everything back in, and I have this as a final expression for my thrust and torque. Okay. So, you will see when Dr. Kothari talks about core rotor, variable pitch core rotor, he will actually start with probably these expressions, okay, and he will find a relationship between CT and your pitch angle, because that is what we are interested in, right. This theta is what is my control input actually, and in here that is inherent inside this TCT, okay, and it is also somewhat part of the CD sometimes if your drag is function of theta, or function of angle of attack, but if it is not, then this part is more or less constant, and torque is actually directly going to change with the way this theta is going to change, which is part of the CT. So, the relationship for CT versus theta is going to come from here and from here, okay, and these are two key parameters which are going to be used for control, CT and CQ. So, like I said, okay, we can use uniform inflow from momentum theory to get the lambda here, okay, that is the most simple thing. If you want to do something more involved, the next most complicated thing is this non-uniform Dries inflow model, okay, where you assume this lambda to be now my induced velocity to be changing with both radius, okay. So, the sigma d and sigma s are the radial locations. So, it changes with both radius as well as your azimuth angle, okay. and so this kx and this whole part is replaced with cosine of psi. And so now my inflow at every location of blade is actually different, I mean both span wise as well as your azimuth wise. So my blade every location is different, and depending on where my blade is, the inflow may be different. So this is actually sort of a empirical solution. Okay. So people observed the flow over the rotor, they did a lot of flow visualization and so on, and they came up with this model which actually meets some of the things. So depending on the skew angle, this chi here, okay, this angle chi, which denotes how much the wake is skewed because of the forward speed. So even in the video of that helicopter you saw, when it was moving in forward flight, the wake was actually, which was initially concentric and nicely helical in shape, used to get blown downstream and it would actually come at some angle. So depending on this angle chi, people have given some empirical formulas, okay, depending on CT or depending on something else, and this chi angle is given by mu by lambda c plus lambda I. Lambda I c is climb if the rotor is in climb, otherwise it will be simply mu by lambda I, okay, and lambda I is actually based on your hover. So using these expressions I can actually have a non-uniform distribution of inflow. This is one simple model. Beyond this there are many other things, dynamic inflow, dynamic wake, free wake model and so on, but we are not going to go in any of those. So these things are all available in literature, any helicopter book actually has all these things actually. So this is, so then what happens, I mean this lambda I goes and sits over here, okay, in the integration, and after the, so all these integrations have to be performed numerically, as you can see. You cannot do this closed form integration on this because your lambda may be varying in a particular manner, theta may be varying in a particular manner, so performing these integrations is actually not easy. You can do it for a very simple case, assuming rectangular blade and certain things and so on, but to have a more generic calculation done, all these integrations are performed using numerical techniques. So normally in helicopter world we use 6-point Gaussian quadrature. Okay. Are you familiar with this thing, Gaussian quadratures? Okay. You are not, okay. So maybe in some of my later slide I will bring in, I mean my later presentation I will bring in a slide on that also, okay. But beyond that you can use trapezoidal rule, you can use any other integration method, okay. So the simplest possible Simpson's rule, trapezoidal rule, all these typical numerical integration techniques can be employed to compute these integrations, okay. So any of the things are actually fine, okay, as long as you ensure that you take enough number of small segments to ensure the accuracy of the integration, that is all, okay. So I have kind of already, we are still have left with 10 minutes and we have already come to blade dynamics part, which was to be covered in the next lecture. So you have any questions, anything you want me to go in more detail of, because we still have 5 to 10 minutes time. Otherwise I can start, okay, I can start with the basics of rotor dynamics, okay. In this let me see, I think it is fine, okay. So no questions?
Solidity, what is the effect of that solidity?
So solidity, I mean as such from control point of view it may not be of great significance, okay, but solidity is a parameter which influences the design a lot, okay. So a rotor with higher solidity, okay, is typically good for hover, okay, but then it may have also higher drag. So solidity as such, I mean is a design parameter which is going to impact the design more than the control. So for control point of view you do not have to worry about solidity, because anyhow I mean you know what rotor you are designing the controller for, okay. So it does not play so much of role for control, but it is important for a designer, okay, because it directly controls the amount of blade area which is there, okay. So to have the same amount of blade area you can actually go ahead with larger number of blades, or you can have a larger rotor. So solidity influences something called disk loading, which we mentioned, thrust per unit area, okay, and disk loading directly influences your induced velocity, because your Vi is inversely proportional to disk loading. So if your disk loading is high, your induced velocity will be it is proportional to disk loading actually, okay. So if your disk loading is high, induced velocity is also high. So for example you saw the tilt rotor aircraft V-22 Osprey, that has actually smaller rotors and the overall weight of the aircraft is very high. So it ends up with higher disk loading, and as a consequence it actually has very high downwards velocity also. So solidity actually more important for design and for other considerations such as, I mean, okay, whether downwards velocity is important for you. For example, if you are designing a helicopter which is meant for search and rescue operation, so if this helicopter goes and hovers, you are trying to rescue a person who is actually drowning or something, and the rotor has very high downwash, that is, it is the air coming from the rotor is very high, it will actually try to blow the person away. So if you are designing a rescue helicopter, then you would want to make it something which has a larger rotor, which has lower induced velocity, so that it will not hinder the operation. Okay. So it has more of it's about a design choice than actually control. Okay. So all right. So now I will start with the rotor blade dynamics. Okay. So what we saw so far was aerodynamics. Okay. So we got an idea of how we can find out thrust for a given geometry of a rotor and how we can find out torque, because these are the two key parameters which are required for control of a helicopter. Okay. So this is an example of rotor hub. Okay, how they are. Okay, we have already seen how rotor hub looks like, and so shall I pass this along? Okay, all of you can take a look at this. Okay, so this is, you can just pass it to the back. Okay. So you can just see how the swash plate is. So this is for a full size helicopter. You can see how complicated and messy, I would say, okay, this entire rotor head looks like. Okay. In this case, it is fairly nice and clean, simple. It's a simple rotor. It doesn't have so many systems and so many sensors and other things built into it. So you can see it's so complicated. Okay. So this is the swash plate for all of them. Swash plate here, and this is the pitch link. In this also you can see the pitch link. Yeah, the pitch link is the linkage which is connecting the swash plate to the rotor blade. So here is pitch link. All these helicopters you can see pitch links. Okay. So this swash plate actually has two parts, as you would see, a part which rotates, other part which is stationary, and they are in between them. Actually there is a sort of bearing which allows smooth rotation between them. So the lower part remains stationary, and the top part which is connected to the pitch link spins. And so this is for BO105, Sikorsky H53, this is for H60, and this is EC532. All these are different helicopters actually. Okay. And this is the key element. This is the element through which you are going to give the control input to the rotor. Okay. So this, how this input actually translates to the overall dynamics, is very important for us. So normally a helicopter rotor blade has three articulations. Okay. So in this cartoon what you are seeing is that the blade, this person can actually move the blade up and down. Okay. This is called blade flap motion. Okay. Flap motion. Then it can be also moved sideways, that is in the plane of the blade. So if you see this particular helicopter, it actually has a hinge which enables the blade to move freely in the plane. Okay. So once I get it back I will show it to you. So it also allows this in plane motion, and the third is the pitching motion or the feathering motion. Okay. And that is what actually is achieved by the swash plate and the pitch link. So when the pilot moves the stick, either the cyclic stick or the collective stick, he actually makes the swash plate either move up or down or tilt to the side or to the front and back, and that tilting gets translated to the changing of pitch angle of the blade through the pitch link, and as a consequence the blade can do feathering. So the blade can actually feather or pitch about its axis because there is a bearing here. Okay. So this is actually close up view of the hub of the helicopter. So here you can see what we have shown here is, this is a nice hinge given here to enable the flapping of the blade. This is another hinge in the, this is like a pin joint given here which will enable the lead lag motion. So this is called flapping motion, this is called the lead lag motion, and the other is the feathering or the torsion or pitching motion. So torsion motion, pitching motion or feathering motion is what is the third motion. So for that you are given a bearing here. So this is a bearing, and here you will be a pitch link which will connect to the blade, and that pitch link will push the blade to do the feathering. Okay. So I think I will just wait for the helicopter to come back. I think we will stop here, okay, because